Question 3 is a question covering material from the second exam, and this is stuff about lactones, which are cyclic esters, meaning a double bond and an O that are part of some kind of ring. So like this, it's a ring, but there's an oxygen in it, and a double bond O, a single bond away. So your main way of making lactones is taking a carbon chain where on one end there's a carboxylic acid, on the other end there's an OH, and then you treat it with H+. So the first step of the reaction is always going to be the same. You have H+, something's going to get protonated. If you ever see H+ over the arrow, that will always be true. And between this OH, and this carbonyl, the carbonyl is the clear winner for getting protonated. Why? Because if we consider the resonance of this double bond, we know it always resonates up, and that would make this oxygen minus. So that oxygen is always the one who's going to go out and grab protons if he has the option. And so what you'll end up getting now is the OH in the bottom left, the same, but now you have double bond OH positive. Whenever you protonate something, typically it becomes positive. Unless it was starting out negative, in which case it would become neutral. So now I have this. Now the next step is, whenever you have a double bond OH positive, something is going to want to attack that carbon. And what has the electrons to do that attack? The OH over here. And this is why the ring forms. So this OH is going to use its electrons and come down and attack there, and these electrons will swing up to the oxygen. And now I'm going to make a ring because I'm having one end of the chain attack another end. So how do we figure out how large that ring is going to be? Number your carbons and whoever's doing the attack. So in this case, this oxygen is using its lone pair to do the attack. So I'm going to start by numbering that 1 because he's forming the ring by using his electrons. And then I have carbon 2, 3, 4, and carbon 5 is where it's being attacked, so that's where I stop numbering. You number from where the attack is starting to where the attack is ending. So I am making a 5-membered ring. And I'm just going to start by drawing that 5-membered ring. Now remember, the oxygen was the thing doing the attack, so the oxygen should be part of that ring. And since this hydrogen was never touched, it should still be there at the end, meaning that oxygen is positive because whenever an oxygen has 3 bonds in this course, it's going to be positive. Okay, now I just have to fill in the numbers. So I said oxygen was 1, 2, 3, 4, 5. Now I just have to fill in what's missing based on my numbering. Carbon 2 had an ethyl chain on it, 2 more carbons, so 1 and 2. Carbon 3 had a methyl, so 1 there. And carbon 5 was the carbon that got attacked. It had 1 OH to begin with, and now it has a second OH because that came from the double bond OH positive that we moved up. So now we have this. Now, we said we're supposed to make a cyclic ester, right? Where there's one oxygen in the ring and then a double bond O next door. Well, this isn't a double bond O yet, so we need to get rid of one of these oxygens because we only had one double bond O, not a double bond O and an extra OH on it. So we want one of these OHs to leave, and we also want to neutralize this oxygen. So what you're going to do is you're going to do a proton transfer. Have one of these 2 OHs grab that proton and neutralize the oxygen in the ring that was positive. And now you have H2O positive on carbon 5, the oxygen in the ring being neutral, the ethyl, the methyl, and then the other OH. And now, again, our goal is to make a double bond O coming off of the ring. So if this H2O positive is a good leaving group and it wants to leave, something has to form a double bond to kick it out. Now, the oxygen in the ring could make that double bond, but then it would become double bond O positive, and there's no way to neutralize that because it has no hydrogens to pull off. So whenever you're trying to form a double bond O, use the thing that you can deprotonate so it's easier to neutralize. So this OH will swing down, and this H2O positive gets kicked out. And now I have my 5-membered ring with a methyl and ethyl, oxygen, the H2O is left, and I have a double bond OH positive again. And this is what I was trying to say about which one should be used to, which oxygen, the one in the ring or this one, should be used to kick out the H2O. Because this is very easy to make neutral. You just deprotonate that hydrogen. So some base comes in, possibly just another molecule of water, and that will grab this proton, neutralize your oxygen, and so your final answer is a 5-membered lactone, meaning again a cyclic ester, a carbonyl on one carbon, and next door is an oxygen that's part of the ring, with an ethyl here, a methyl there, and so that was choice B on the exam. Okay, so this was your answer.